So, in the last lecture we discussed about some of the examples where we could pick up easy problems to compare the static and kinematic theorem results, and we have understood that by selecting a proper mechanism, by selecting a proper appropriate admissible bending moment distribution, we could land up in the same collapse load whether you follow the static theorem or you follow the kinematic theorem. In this lecture we will pick up again examples where we will slightly go further beyond to understand how one theorem depends on the other in certain examples. Okay. So, example 1, I will pick up a fixed beam with UDL W. So, the span of the beam is L, and we already know the degree of indeterminacy of this beam is degree of indeterminacy is 2. So, you need the number of plastic hinges as 3. Possible locations are A comma B, that is A and B, and somewhere in the beam AB, which will be obviously the point C where the bending moment will be maximum. Can you guess where the bending moment will be maximum in this given beam? Center. So, I can mark a point C here and say that is going to be the possible point where my plastic hinge could form. Okay. Let us solve this using both the methods. Let us say using static theorem. Static theorem wants the structure to be in position, it wants the loading to be applied, and now it wants a bending moment distribution for both external forces and internal reactions. So, let us draw the beam. Let me draw the bending moment diagram for both cases. So, we all know that if the beam would have been simply supported for a given loading, the bending moment diagram is going to be a parabolic, is it not, whose value at the center will be equal to WL square by 8, that is this value. Okay. And because of this there will be fixed end moments generated at these fixed supports, and that value is going to be equal to WL square by 12. Okay. So, as usual this is going to be negative and this is going to be positive. So, I want to flop this. Okay. So, if I do that, I get a figure like this. So, obviously this portion will be negative, this portion will be positive, and this portion will be negative. So, this is a net bending moment diagram here, is it not? So, the possibilities of plastic hinges in this sections are the following: one I can have here, one I can have here, and one I will have at the center, is it not? So, I should say 2 MP is equal to WL square by 8, is it okay? Because this is WL square by 8, this is 1 MP, this is another MP, agreed? Now, you must understand that I must select sections in such a manner of maximum bending moments where the structure will become a mechanism. Okay. So, I have selected the sections of maximum bending moment, the structure has been made to a mechanism. To make it the mechanism I need 3 hinges, I have made 3 sections where the bending moment is maximum. Okay. So, 2 MP is WL square by 8. So, 16 MP by L is WL. Okay. WL can be called as WC. Okay. This is kilonewton per meter into meter, becomes a load, okay, WC. So, 16 MP by L. Let us solve this problem using kinematic theorem. This may deflected profile, this is not the bending moment diagram, okay, it is a deflected profile, the maximum deflection will be at the center. So, hinges will form here, will form here, will form here as well, is it not, 3 hinges, this is an assumed mechanism. So, as usual I will call this value as delta, this is theta and theta, and this is going to be 2 theta. Okay. So, we should say external virtual work should be equal to internal virtual work. Now, external virtual work in case of UDL is nothing but the force multiplied by this area. So, half L delta WC, is that okay? Which is going to be MP times of theta plus 2 theta plus theta, is that okay? So, 4 MP theta. I can also say WC into L into delta is 8 MP theta, is it okay? I can even call this as WC into delta is 8 MP theta, because WC into L is capital WC, and delta and theta can be connected from the figure. Theta for small angles will be delta by L by 2, which is 2 delta by L. I substituted here. So, WC into delta is 8 MP into 2 delta by L, which is 16 MP by L. I get the same value here. We will do another example where we have got to slightly do some static indeterminacy calculation for finding out the elastic bending moment distribution. We will pick up this example of a continuous beam with central concentrated loads. So, these are the points A, B, C, D and E. What is the degree of indeterminacy for this problem? These are all hinged supports. For the modified value, neglecting the axial deformation, they will have only one vertical reactions. There are 3 reactions unknown, there are 2 equations available. What is R in this case? What is R in this case? R, yeah, R will be 3 minus 2, which is 1. So, the number of plastic hinges required will be only 2, okay, where they will form. To solve this problem by static theorem, I must first know the bending moment distribution. The bending moment distribution for the span AB and span BC is very simple, it is WL by 4, simply we can draw. But to draw for this entire span ABC, what are the moments at A and C being simply supported? They are 0, okay, there are no moments, but there will be a moment at B here. I want to find this moment now, okay. Since it is statically indeterminate, by one order I cannot use it by simple equations of equilibrium. I must do a method by which I can find out MB, right. Let me do moment distribution method. We are not discussing this method here, but I will briefly explain this here, okay. We will now do moment distribution method. To find out the moment at B, okay. So, it is a very simple method. These are the joints, which is A, B and C. These are the member designations. I call this as AB, this is BA, this is BC and this is CB, okay. I would like to write down the distribution factors, distribution factor. distribution factor is given by k by sigma k. This is generally done for joints which has got at least 2 members, at least 2 members. So, in this beam, which is the joint which at least have 2 members connected? B. So, I should do joint distribution factor for the joint B. Generally K is given by simply EI by L. I am looking for the bending stiffness. This is the bending stiffness. Is proportional to EI by L. Okay. So, I am saying E and L of AB and BC are same. Okay. Even I, that is the cross sectional dimensions of AB and BC beams are same. So, I can simply say distribution factor K of BA will be, let us say 1, K of BC will also be 1, that is EI by L. So, sum of K will be 2. So, distribution factor for BA will be 1 by 2, which is 0.5, and for BC is again 1 by 2, which is 0.5. Remember, the sum of distribution factor at any joint, be it any number of members connecting the joint, should be always equal to 1. So, I am writing those values here, and these are not available for A and C, because you should at least have 2 members to connect this joint. Agreed? I can remove this. Is this clear? It is very briefly and quickly I have explained this. Okay. Now, I want to write the fixed end moments. Let me draw these lines, it will be easy. Fixed end moments. If I have a member subjected to a central concentrated load, let us say P, okay, equal L, this value and this value, or standard available, which is PL by 8 and PL by 8. If I have a member of L subjected to UDL of W, then these are equal to WL square by 12 and WL square by 12. Okay. Now, I consider clockwise moments as negative, some sign convention I have to follow. Okay. So, I pick up this problem, I say initially AB is simply supported, but I am trying to find out the fixed end moments. So, I must convert these supports to fixed, I have to assume them to fixed, then release it later, I will show you. So, this is A, this is B, central load W equal. So, now this will be MBA and this will be MAB. Okay. You may wonder how I am marking these arrow directions. Okay. How I am marking this? Hold the finger here, take the moment of this force about this point. So, this will have a direction like this, is it not? This will oppose it. Hold the finger here, take the moment of this force about this point, it will rotate like this, this will oppose it. Okay. So, I said clockwise is negative. So, I can say MBA is minus W L by 8 and MAB is plus W L by 8. Okay. Similarly, let us do it for BC also. Do you agree? Same, is it not? Let me write down these values here, right. So, MAB is WL by 8 minus WL by 8 plus WL by 8 minus WL by 8. Is that okay? Right. In original beam, joint A and C were simply supported. What are the moments at the simply supported joint or a support? They are 0, whereas the fixed end moment caused by this load at this A is plus L by 8, is it not? So, I have to make it to 0. So, I must say balance. So, if it is plus WL by 8, I must say minus WL by 8 to make it 0. Similarly, this will be plus WL by 8. Do you agree this? Once I balance this, I should also do what we call as a carryover. Carryover is 50% of this. So, I must carry over this with minus WL by 16, 50% of that, and this is plus WL by 16. Is that okay? Now, if I say this is balanced 0, this balanced 0, and this is also balanced, but the value is not 0, they are balanced, okay, but the value is not 0. Now, this is nothing but your MB, okay. What is that value? L by 16. So, I am marking it here. Now, I have to add this. So, these two values, let us add this. This is not WL by 16, I have to add these two, no. Can you give me what is this value? This and this together, because there is a value here, there is a value, I have to add this, nothing but sum. Three WL by 16, is it not? Is it not? WL by 8 and WL by 16. So, I write it here. Is that okay? Just to find this value, we have explained this thing. This method is what we call as moment distribution method. Okay. Suppose if they are not balanced, then we have got to again do the balance and carry over, keep on doing it for n number of cycles until the moments get balanced. Okay. So, I will remove this, I do not require this anymore. What I wanted is only this value. Now, we got this value. Now, let us do the static method. I am drawing both the positive and negative bending moment on the same side, instead of flipping it later, I am drawing on the same side. Okay. So, if I do this first for here, what will be this value? WL by 4, is it not? And similarly, this value will also be WL by 4, correct. Then this value will be, this value will be 3 by 16. Is 3 by 16 greater than WL by 4 or less than WL by 4? Check 3 by 16, what is the fraction? It is 0.1875. See. So, WL by 4 is 0.25. So, this ordinate will be lower. So, this is 3 WL by 16. Okay. Now, the bed bending moment diagram is this. Is it not? This is my net bending moment diagram. Now, this value is WL by 4. I want to know what is this value. Can I find out that? It is very simple, because for L it is 3 by 16 WL, for L by 2 this can be easily found out. Can you tell me what is this value? I call this as Y, tell me what is this value. This is L by 2. So this is 3 WL by half of this, no, 32. Okay. How many plastic hinges this section can have? 2. One is for sure at B, let us say for example. Okay. One will be here or here, is it not? Since the structure is symmetric, it can have more than R plus 1 also, which is called as over complete collapse. Okay. Now can you tell me what is this value? I call this as Y2. This is WL by 4, this is 3 WL by 32, I want this value. Five WL by, yeah. Okay. Now if I agree that the plastic hinges will form at D, B and E, for plastic hinges formed at D, B and E, using static theorem, I can say that MP plus MP by 2, this is MP by 2, why? This is MP, okay. MP by 2 plus MP is equal to WL by 4, can I say that? Because this is WL by 4, is it not? So can you tell me what is WC? Good. Okay. This is for the span AB. You can also try to do the span BC, you will get the same story here also, is it not? Span BC, this value will be WL by 4, this is going to be MP, is going to be MP by 2, get the same equation, you get WC. So if you got a combined mechanisms like this, analyze them independently and look at the maximum value. Why? This is by the static theorem. Static theorem will give you WC is, this WC is also 6 MP by. So static theorem will give you WCs which are either lower than true collapse load or to the maximum equal. So look at the maximum, I compare these two, both of them are equal, so WC is equal to actually 6 MP by. This is by the static theorem. Let me do this problem by the kinematic theorem. Where are the hinges forming? For the span AB, it will form here and here, is it not? for the span BC it will form here and here. Why it is not forming at A and C? They are simply support they are structural hinges already. Okay. If you call this as delta and theta, this is 2 theta again, this is 2 theta again. I can do it for span AB separately. What kind of mechanism is this? This is a beam mechanism. Okay. Span AB, it forms a beam mechanism. How many hinges are required? You require 2 hinges, is it not? So, you get 2 hinges here. It is a complete collapse, it is not a partial collapse. Okay. So, W into delta is going to be equal to MP into 3 theta, is that okay? 2 theta here and 1 theta here. So, we all know theta is also given by delta by L by 2, which is 2 delta by L. So, substituted here WC into delta is MP 2 delta by L. So, WC is 6 MP. This is for the span AB. Let us do it for the span BC. Virtually it is same. Is it not? It is going to be repeatedly same actually. So, you get both the answers same. So, WC is 6 MP by L. Okay. Now, from this quickly one can think about what is the design, what we are worried about. Okay. Let us pick up this example quickly to demonstrate how do we do the design from this. Let us rub this. See, for this example let us say we know that WC is 6 MP by L. Okay. We also know the load factor Q is WC by WW. WW is nothing but the working load which we already know. Q can be taken for different load combinations from the code. So, Q is known to me. For example, let Q be 1.5. So, I know WC. Okay. So, left hand side is known to me, L is known to me, I will find MP, and MP is nothing but S into ZE into sigma y. Sigma y is known to me. Okay. Now, I will select a section of rectangle, I, box, tube. So, I know S value. Okay. Right. I already know the ZE value for all of them. I design. Is it not? Because S will be a function of, or ZE will be a function of B and D or diameter and thickness etc., depending upon the section what you want. So, you will equate this, because MP is known, equate it here, MP is equal to this, pick up the section, choose S 1.5, 1.15, S is the number for a given section, ZE is a parameter of B and D or etc., you will find B and D, that is design. Okay, that is plastic design. It is as simple as this, is it not? We will take up another example. Where the problem is slightly tricky. Now, I will take a propped cantilever. this is W yeah A B. Now what is the degree of interdependency of this problem? There are two unknowns here, vertical and moment, one unknown here vertical 3 minus 2, so it is 1. So how many plastic hinges you need to make it as a complete collapse? 2, to make it as a mechanism. Where they will be formed? For sure one will happen at A, no doubt. Can the other one happen at B? Next hinge. Why? Because simply supported. So there will be a section C which we do not know where this will occur, because it is the point where the bending moment is going to be maximum. Okay, so we should find that point. Are you getting the question here or not? So it will be at C, which we do not know, we want to find the point C as well in this problem. Okay. So if I do, for example, if I directly do kinematic theorem to this, kinematic theorem says draw a hinge location and form a hinge here, form a hinge here, external virtual work, internal. So I should know delta, I know theta. Now if I do not know this, I cannot find delta and theta, is it not? So I cannot apply kinematic theorem to this. Okay. Can I apply a static theorem to this? I do not know what is the bending moment at this point, is it not? So let me do bending moment xx which is WC L by 2 into x, that is the reaction here, minus WC L x square by 2, that is the bending moment at x, any section. Okay. Section, look at the right, the reaction multiply with the distance and this value multiply with the distance. If we try to draw the bending moment distribution for this, one will be a parabolic, the maximum is occurring here, one will be a linear, is it not, 0. So this is going to be MP and this is going to be MP, correct, because two hinges and this distance is x, of course. Can you tell me what is this if this is MP? For L it is MP, for x what will be this value? What is this value? Yeah. Okay. So the total bending moment at this point should be equal to this to make it as a mechanism. So there is no L here, no, there is no L here, there is no L here, please, it is WC x square by 2 only, WC x square by 2. So let us say now WC x by 2 L minus x. So MP will be now equal to WC L by 2 x into L minus x by L plus x. Now I want this MP to be maximum, is it not? MP will be maximum because plastic hinge is forming here. So I should say the differential of this with respect to the variable should be set to 0, to make it maximum for maximum MP. Differentiate this expression, see what happens. So, it is basically d by dx of Wc by 2 Lx of L minus x by L plus x. So, already we have an expression here, you can use this equation, substitute x as 0.414, get the value. You have x is 0.414, get the value. How much is that? So, Wc L by 2 0.414 L minus 0.414 L by 1.414 L. Substitute this, is it not? No. No. How much? Come on, this can be easily sorted out, no? This is going to be 0.0857 Wc L square. Check. Are you getting it or not? Okay. So, if I say WCL is capital WC, so MP is equal to 0.0857 WCL, okay, I can say this. Small WC into L is capital WCL. So, can I say what is WC? I am interested in WC. What is WC? What is WC? So, MP is equal to 0.857 WC. Sorry, yeah, 11.65 66 MP by L. Is that okay? This may collapse, and the hinge will occur at a distance of 0.414 from the propped support, not from here, from the propped support. So, it is not at 0.5, it is away from 0.5, that is why I have drawn the figure like this. The center is not at 0.5, okay, it is away, this value is more than this, okay. Now, I can use kinematic theorem to find out MP. How? See here. This delta, this theta 1, this is theta 2. and this distance already I know, which is 0.414 L if this is L. Okay. So, what is the external virtual work? Half into base into height into WC. Internal virtual work will be MP of theta 1 plus theta 1 plus theta 2. Is that okay? Okay. Okay. So, half WCL into delta is MP of 2 theta 1 plus theta 2. Theta 1 is equal to delta by, this is how much? L minus 0.414. How much is that? 0.586. Okay. And theta 2 is delta by 4L. So, substitute here, cancel for delta, get me what is MP. Because WC into L can be taken as capital WC. So, half capital WC into delta is MP 2 theta 1 plus theta 2. So, theta 1 is known, theta 2 is known, you can compare them, substitute them, find out what is MP. Tell me what is MP. How much? You are using calculators, no? How much is that? You will see that this will be also 11.66 MP by. Exactly same. So, in this example we have understood that kinematic theorem in certain cases cannot be applied directly because you do not know the location of the formation of the hinge. So, both the theorems are equally important to understand. So, in this example classically you have understood that we have used static theorem first to find out the location where the hinge can form, then we have verified it with the kinematic theorem. Is that clear? So, you cannot forego any one theorem thinking that both theorem will give me the same answer. So, I can study only one theorem and be done with it. No, certain examples like this static theorem plays a very important role to really find out what is the value of or where is the point of occurrence of the maximum bending moment. Okay. The next class we will talk about some design example and depth of elastic core calculations, where we do plastic design really for a simple beam and a frame, and we will demonstrate it. Once we understand that, we will talk about theories of failure. Okay. Then we will move on to accident loads and tubular joints. So, that will end the module 1, maybe in another 4 or 5 lectures maximum, but you have got to be faster in calculation, otherwise we will be delaying things. Okay. Thanks.